Zombie apocalypse.
Okay, so this time let us talk about design and allowable flexural strength of an I shape again, no? But this time let's consider non-compact or maybe a slender flange. So let's get ready to be neurorized. Suppose that we have this problem, a 7 meter simply supported beam carrying a uniformly distributed dead and live load of value 7 kilonewton per meter and 3.1 kilonewton per meter respectively. So the longer unbraced length is 4.5, meaning there is a unbraced condition, naglagay tayo ng stiffener that is located 4.5 meters from any support, ano? Kasi simply supported naman, leaving another unbraced length of 2.5 meters. So using a section that is W21 by 48 under ASTM A992 grade 50 standards, so let us determine the flexural and the demand capacity ratio under flexure for ASDN Lrfd. Now let's talk about the solution. Okay. So again, taken from the AISC database, so you will get this following. So again, the same discussion goes regarding the parameters. Again, pag hindi ito sinupply, we can calculate naman each of the values as already discussed in my past video lectures using the basic dimension that was W21 by 48 in conversion to metric that is a W530 by 72. Okay, so to continue, okay. So, by this given, no, sinabi naman dito na 4.5 meters shell base length. Now, you have to notice that there is X markings. The X markings will determine the unbraced length position. So, sinabi ng problem kanina, the span is 7 meters. So, indeed, this is a simply supported span, but X mark will determine the unbraced length, no? So, sinabi dito, the unbraced length is 4.5 meters. So, leaving another unbraced length of 2.5 meters. So given the specs of ASTM A992 grade 50, again, we know this that FI is 345 megapascal. Again, I have already a video lecture with the presentation of the common parameters of ASTM standards related to steel. And again, it was given the dead load and live load as 7 and 3.1 kilonewton per meter respectively. So again, let's start the analysis since the data does not have any value for the height cleared from the fillet. So again, by the illustration as shown by AISC manual, steel manual, it is in terms of T. Again, T is our H. Okay? So again, H is defined as in ANSI AISC 360-10, the distance that is in terms of height, it was actually clear from the flange and the fillet radius, or simply the fillet region. So, using that, we know that this is K design in theory. So, to compute the H, that is D minus twice of the K because it is located top and bottom. So, leaving an answer of H of 475.8 millimeters. Okay, so lagi natin sisimulan na, no, yung tinatawag nating check for compactness. Again, as mentioned in 506.6.2, medyo makikita nyo to, no, sa user note, it was identified that W21 by 48, which is our dimension in question, okay? So it was shown here that it is a part of being non-compact flange, okay? So it means under the criterion of F of 345 or simply grade 50. So meaning we will expect from this given na ito ay maging non-compact yung flange. So let us try to verify kung totoo ba itong 21 by 48 so will be a non-compact flange. So by using the criterion set forth by the NECP 2015, which is all just adapted from the code from ANSI AISC 360-10 and or AIS is still manual since yung code ng 360-10 and actually the latest was 360-10 360-16 is already part of the still manual version 15. VCC-10 is solely manual version 14. Okay, set forth again by the code, no? Gagawin natin. Since this is a it is actually a default dimension from the W shape is W21 by 58. So meaning we will understand number 1 for the anti-stiffen condition and as well as the condition for number 9 to qualify the B over T or the BF over 2TF in correlation to the function of the width of the flange and the function of the height cleared from the flange and the region of fillet all over the thickness of the web. So we will use again this criterion, So this time we will try to involve the compact and non-compact. So again, if you will take a closer look on this, sinasabi natin compact kapag lambda is less than lambda p. Okay, pag non-compact, if lambda is in between lambda p and lambda r, Yan yung consideration niya. So kapag more than ka naman sa lambda r, so meaning you're under slender. So ulitin ko yung una, this is the compact. Okay, this is compact. The second one is non-compact. Okay, and being compact and non-compact considers both as non-slender. Okay, automatic na non-slender siya, and lambda is more than lambda r, that's what we call slender section. Usually, sa slender section, dyan nagpo-fall under yung mga columns. Okay, using the criterion, we have to check for compactness in the use of lambda p for the B over T. Now, upon computation, so you found out that the lambda becomes more than lambda p. So therefore, there is next checking that we need to perform. Alamin na natin kung ito ba ay non-slender na non-compact or is it totally a slender. So therefore, we have already exhausted the criterion for the pointer tail square root of that constant, which is A over Fy. So this time, let us compare it with the lambda r. So pag lumagpas ka pa ng lambda r for the check for compactness under the flange, so therefore we can conclude that this is slender. Otherwise, this is non-compact. So upon checking, we found out that it abides that the lambda is not more than lambda r. So we can conclude that the lambda is in between lambda p and lambda r. So we can conclude already that this is a non-compact flange. And doing the check for compactness for the web, and dun pala sa lambda p, nakita nyo na nagko-compact na siya. So therefore, this is a compact web. So in conclusion, we will try to understand the flowchart from the non-compact flange. So ano kayang code ang de-describe ng kanyang condition in computing the capacity of the section as well as the demand capacity ratio under Flexural. Now, let us understand the check for unbraced length. So, okay. So, by this, according to the code, kasi non-compact tayo, so this will apply. Tandaan natin that there are two possible sets of computing LP and LR. That is one for the compact and one is for the non-compact flange. So, of course, we need to be vigilant, kung saan tayo mapupunta. And the other one for the non-compact web. Okay, so tatlo pala siya, So therefore, as we continue, so to compute LP, so this will be the case, and this for LR. Now, we have the complete criteria for this, and we need to consider that C is equal to 1, kasi yung section natin is a doubly symmetric shape. So, pag sinabi nating doubly symmetric shape, so symmetrical along the X and symmetrical along the Y, yung ating section, kaya doubly symmetric. So, we will compute this, Ang ating L sub P is 1,788.2596, while the L sub R, the maximum unbraced length, so where L sub P is the minimum unbraced length, so as shown, so you can compute it anyway using the values of like the J, Okay, you can use also as part of the computation L sub R, which is S sub X, and also the R sub TS, the effective rate of gyration, and the H sub naught, or the Flange centroids. So therefore, you can get this, and by this, no, we can configure out that LB is in between the minimum and then the maximum unbraced length. So we will take a closer look. Ano kaya ang nominal moment na mag-exist sa ganitong criterion? So after checking for the lateral support type, or what we call the unbraced length condition, so we follow it with a check for flexure. Since this is the main question of the problem, but of course don't forget there are more possible modes to check, no, not only flexure. There's also torsion and also shear and deflection. So for the meantime, we are being delimited to analyze it under flexure. So what is the code behind, no, in checking the flexure? Ano kaya ang criterion ang nag-satisfy para masabi natin kung ano yung flowchart na magagamit? Note that we have a non-compact flange, and this is a doubly symmetric shape. So under section 506.2, that fits the description. So doubly symmetric I-shaped members with compact webs, yes, we already found out, and non-compact or slender flange, which is we qualify on this. Ngayon, as mentioned also, as set forth by the code, so doubly symmetric I-shaped members bent about the major axis, which is as we apply the load above, no, that is gravity pulled, so it rotates about the x-axis, so therefore it is under the major axis. I already explained multiple times in my past video lecture how do you qualify if the section is being loaded in the major axis or the stronger axis, or in the y-axis or the weaker axis, or the minor axis. Okay. Now, so by this, this is qualified. So how do we select the nominal moment? So it shall be the lower value of the onto the following. First is to check first the lateral torsional buckling. So that's the number 1. And compression flange local buckling, which is criteria number 2. So which is, ang minention naman si 506.3.1. So for lateral torsional buckling, the provisions of section 506.2.2 shall apply. Ito yung ginagamit natin for compact sections. So ibig sabihin, uulitin natin yung ginawa natin before under lateral torsional buckling, but that is to cater up the condition for having a non-compact or slender flange bent on the major axis. So under 506.2.2, so the way we calculate that, no, ito yung code natin before. So if you will take a closer look, ito yung nag-qualify sa atin because LP, LB, and LR is in between. LP and LR is nandun sa extremities no LB, or in short, our brace length or unbraced length, I mean, unbraced length L sub B is in between LP and L sub R. So ito yung equation natin na gagamitin, 506.2-2, to qualify the nominal moment, but don't forget that it is less than or equal to the plastic moment. So, ito yung mga kukumpitin natin, gagamitin natin equation to calculate the nominal moment. Okay? So, before we move on to the next discussion, note that the Fys sub x is simply the yield moment. Okay? So, I already provided discussion on this, how to calculate the yield moment. So, in short, I can simply say that the nominal moment is equal to C sub B, quantity, the plastic moment, minus the plastic moment, minus the 70% of the yield moment, okay? So, and then multiplied by the constant LB minus LP all over LR minus LP. So, pakiingatan na lang siguro yung pagka-compute nito kasi ito unahin nyo muna. Itong dalawang to before nyo i-deduct sa MP, and then before you multiply it by the coefficient of bending. Now, in calculating C sub B, so ito ulit yung equation natin, already discussed before. And then yung tinatawag natin monosymmetric constant, R sub M, will be dependent on the condition where our beam is doubly symmetric, then it is conservatively used as 1.0 for doubly symmetric beam. So therefore, ang ating titignan nandito yung Mmax, MA, MB, and MC that is found within the unbraced length as mentioned in this code. You know, so it was mentioned clearly inside the unbraced segment in Newton millimeter. So Mamaya i-convert natin into kilonewton meter para medyo lumate-late yung mga value. Of course, this is dependent on the load. So if we were to read also this won't apply kasi sabi dito, CB is permitted to be conservatively taken as 1.0 for all cases. However, this will eliminate the potential precision of the calculation kasi we will not have an exact value of 1.0 for this computation. So for me, I am not using C sub B. So to take into account that it is always taken as 1.0, since I have to be careful onto the value of C sub B because to the reason of the evolution of the basic code from the C sub B before into this equation, since it was found out that for nonlinear diagram, so the C sub B should be taken care of. And also, as mentioned here on the user note, no, for W symmetric members with no transverse loading between brace points, of course, it is reduced to 2.27. It can be proven naman in calculation. Okay, so let us compute the function of the lateral torsional buckling, or we will call it as LTB. So computing yield moment, so we will get 524.4. We have the property for the sectional modulus. And for the plastic moment, that is the plastic sectional modulus J sub x. So therefore, we'll get 603.75 kilonewton meter. Now, we compute the coefficient of bending. So we understand first the weight of the steel beam itself. So in accordance to this, 72 kilogram per meter was utilized. So if this is not given, you can calculate this eventually. And I have already discussed kung paano siya kino-compute. So we convert 72 kilogram per meter into kilonewton per meter. So we already shown before in the last video lecture on how did we arrive to this 9.81 over 1,000 in conversion from kilogram to newton to kilonewton. And then we will have a beam weight of 0.70632. Medyo conservative ko muna yung value, so I considered all values so that we can have, a more precise computation. So, computing the W, ulitin lang natin, sa pag-compute ng coefficient of bending, it doesn't matter kung gagamitin mo approach is ASD or LRFD, since they will give you the same value, since yung load na value niyan is magka-cancel out naman onto the equation, since W sub U is a function of the moment. So you can do it by derivation, then you will notice that W sub U or even W will be cancelled out inside the equation. But here, for the purpose of discussion, I have calculated CB in terms of LRFD so that it will give way to other calculations that might be needed. So, sinama ko na rin. Para later, medyo konti na lang yung ating kukumputin. So, we will arrive to a W selection of 14.20758 for kilonewton per meter, where the subscript of U designates an LRFD situation. Pag walang U, so it means that is ASD. So drawing for the cut segment. So ulitin natin, we consider the larger unbraced length, which is 4.5 is more than 2.5. So by that region, yun lang yung isasama nating region, okay? And then you have to divide it by quarter points. So may 4.5 over 4 kayo nakikita dyan. So representing moment at A, moment at B, and moment at C. And notice that the maximum moment is within the region of the unbraced length. So makakasama yung moment maximum na W L squared over 8 sa criteria ng maximum moment. Pero kung i-consider nyo yung 2.5, kung kukumpitin nyo rin yan, later I will provide the values. So kung ito yung quarter points, i-divide natin sa 4, okay? So ito yung magiging mga points nito. So pwede ito yung moment at ito sa moment A, or pwede mong gawing moment C yan, pwede pagbaliktarin, pero ito hindi pa pwede baliktarin. Ito yung moment B, ito yung moment C. Pero kung ginawa mo moment C sa unahan, ito yung magiging moment A. But don't forget, yung maximum moment nasa labas ng range. So therefore, ang lalabas sa maximum moment dito, under that region, is this value. So dito siya lalabas. So you need to compute that moment point. Okay? So as we continue, so ito yung parang magiging kakalaruin lang natin, ito yung magiging maximum moment, okay, for LB, that is 2.5. Kasi ang description ng Mmax within the unbraced length na ina-analyze. Okay, ito yung violet region na kikulayan ko. Kapag kinonsider nyo, yung 2.5 meter as the unbraced length. Kaya ang general rule dyan, ang LB na pinakamalaki, siya ang gagamitin nating analysis portion. So, you will notice that consistent yung equation. So, I can derive an equation out of this. And then, substituting 4.5 over 4 on each situation, you can have an equation. And then, we can have the answer for point A, B, and C and maximum moment. But, actually, pwede nyo gawin. Drawing na lang yung moment diagram, then trace the point. So, that's it. So, this will be my equation. So, I derive this based on the derivation taken from this load. So, at x is quarter point, at x is half, and then the next quarter point. So, yan yung dinidescribe ng 1/4. Okay? No, yan yung 4 na nandito. 2 over 4 is 1/2, and 3/4 as 3/4. So, you will get these 3. And don't forget that MA, MB, MC, as well as moment max are all absolute. Kaya kahit negative yan, you will check the magnitude kung saan siya malaki. Take the absolute. And it turns out to be our MU maximum, that is WUL squared, will be our automatic Mmax. Okay? For that statement. So, substituting it inside the equation, so you will get 1.787, that is less than 3. So, we accept CB of 1.1787. Again, if your CB turns out to be more than 3.0, then accept a CB equals 3.0. Now, using the equation, so ito, naka-describe naman dito. So, following all the values as indicated, so just plug it in, then you will get 479.445 kilonewton meter, which is less than plastic moment. So, therefore, we accept the lesser value, which is 479.4345 kilonewton meter. So, this will represent the nominal moment under lateral torsional buckling, or LTB in our sense. Ngayon, if you choose to use the 2.5, you will get CB of 1.4 and a moment nominal of 650.694 kilonewton meter. That is more than plastic moment. So therefore, if that is your LB, then your MN equals MP. But what is the main goal? Di ba we need to get the smallest value? So therefore, this won't qualify as a smallest kasi may mas lower pa sa kanya. Kaya as a general rule, kung wala namang end moment na pwedeng kumonta sa kanya, so therefore, you can choose the larger span. Unless, if we have end moments, just like if you have a continuous beam, it is an option to analyze all unbraced length condition. Kasi malaking participation ang tinatawag nating interlocking moment sa pag-analyze ng ating CB. So, pwedeng single curvature at pwede rin naman na double curvature. So, yung mga similar rotation ba? Okay? Actually, mali yung ikot ko niyan eh. Dapat ganito. Pagka nag-reverse cab na pag ganyan ng kilay na tawag, so that should be like this. So, parang ganito. Tama pala yung kanina. Tama pala yung, sorry. So, equilibrium base nga pala tayo. Yan. This is equilibrium base. So, then you need to compute all possible unbraced length. So, another criterion, sabi ng code kanina, the compression flange local buckling, or tawagin natin CFLB. So, what's the code behind this? Okay, notice that our section is a non-compact flange. So, ito yung magpe-prevail. Pero kung sakali, nagkaroon tayo ng slender flange, usually, nangyayari ito sa built up. Kasi if you will take a closer look and compute all the given W, M, and S section under Fy of 345 megapascal or grade 50, wala kang makukuha slender flange doon. All are non-compact or non-compact lang na flange. So therefore, usually sa built-up mangyari yan, then you will have this kapag naging slender flange. So, ang criterion nga lang ng K sub C, as mentioned here, so K sub C should be in between 0.35. So, tingnan natin yung statement, no? Shall not be taken less than or should be greater than or equal. And then not greater than. So, nor greater than. So, mismo na, mali yung aking nilagay. So, should be not be taken less than. So, meaning, should be in between 0.35 and 0.76. So, less than equal. Kasi, shall not be taken less than 0.35. So, meaning, cases should be more than 0.35. And cases should be less than equal to 0.76. And yung lambda PF, lambda R sub F, is just only the lambda P and the lambda R na na-compute natin kanina under checking for compactness. So, gagamitin lang ulit natin yung values na yun as mentioned here under table 502.4.1 and table 502.4.2. So, ito yung mga na-compute natin kanina ng mga lambda. So, ito yung lambda P at saka lambda R under the flange region. So, computing that, so we will get 598.2629. If you will notice, hindi siya kinumpara sa plastic moment because hindi siya correlated direct dun sa limiting condition as mentioned by the code. So, this moment nominal is 598.2629 will represent the value for the compression flange local buckling or CFLB. Ngayon, meron tayong dalawang criteria. Sabi ng code, choose the least, and then we found out that the lateral torsional buckling condition will prevail. So, the least will be selected, and then we will conclude that the nominal moment is 479.4045 kilonewton meter. So, doon na tayo compute ngayon ng Lrfd and ASD nominal moment capacity, moment capacities, and demand capacity ratio under Flexural. So, under Lrfd, multiplying it by 0.9, tandaan natin that MU capacity should be equal to 0.9 times the nominal moment. So, you will get 431.5451 kilonewton meter. Now, if we will talk about the impression, since our MU maximum is less than the MU capacity na nakumpita natin kanina, if you recall. So, therefore, the value is 431.5451 yung ating MU max kanina. It's 81, It's 87.0215 yung value ng moment maximum kanina under Lrfd. Kung titignan nyo yung WUL squared over 8 or in the moment diagram. So, therefore, you will get a DCR function on reflection of 0.2017. So, ito yung answer natin. So, both are safe. Ulitin natin, kapag less than 1 in Curie, so therefore, that is safe. And more than 1.0, isama natin less than sa 1.0 safe. And more than 1.0 in Curie, that is already unsafe or inadequate. Okay, under ASD naman, so MA capacity is simply nominal moment over the omega B, which is 1.67. Or actually, you can compute it as 0.6 of the nominal moment or simply just like just that value, ano? So actually, they will give you the same. But anyway, we will stick to the 1.67. So therefore, we will have a capacity under actual or rather allowable that is 187.0865 kilonewton meter. Ngayon, para mai-compare natin kung ano yung DCR natin or if this is safe or unsafe, so compute natin yung maximum moment under ASC, which is we just only add the loads, no factoring, unless if there is an earthquake force. So, meron tayong load combination for ASD kapag may epekto na ng wind or earthquake. So, then by computing this, then you will have a computation of WTL squared over 8, then you will arrive to a moment maximum of 66.1887 kilonewton meter. So, that's our MA max. No, ito yung pinopoint out niyan. Okay? So, therefore, as we continue, so, by this, tandaan nyo, no, yung MA max natin is less than sa MA capacity natin. So, we can simply say that the flange is safe. Or rather, the W21 by 48 is safe. So, capacity mo more than sa maximum. Then, by computation of the DCR or demand capacity ratio, you will get 0.2306 as a value. Pero, as of today, may mga napansin na tayo based from the discussion on the previous. Now, you will notice that the LRFD versus ASD, okay, lagi nyo po makukuha we are talking about flexure, we are talking about flexure or flex, okay? The DCR under flexure and the DCR under flexure for LRFD, kailangan ito yung ma-abide natin. Lagi po mas mataas ang demand capacity ratio ng flexure ng ASD kumpara sa LRFD. So therefore, ang situation is like this. Pwede maging safe both sides. Pwede maging safe sa LRFD, tapos pwede maging unsafe. Okay, unsafe sa ASD, just like what happened on the past video lecture. So, pwede rin naman na maging unsafe ka dito sa LRFD and then more unsafe ka sa ASD. Ang hindi lang pa pwede mangyari dito, ito yung hindi pa pwede, na yung LRFD mo nag-unsafe, tapos nag-safe ka dito sa ating condition. So, itong combination ng dalawang to, ang hindi pa pwede mag-exist. Kasi, lagi na-observe natin, or nako-compute naman, na yung DCR na ASD under flexure should be always more than the DCR of the flexure of LRFD. We already proven that in the past video lecture, na nag-unsafe ka sa ASD, pero safe naman pala sa LRFD. So, you will now realize how very important LRFD is in our design, since yung dati palang safe sa ASD, safe pala sa LRFD. Is it really safe? Well, the code will say, based on history, it is safe because meron ang mga overestimated value in ASD that we need to understand. That's why LRFD exists. Katulad ng C sa B, na magkaiba sila ng value pero na-overestimate ng C sa B ng ASD ang actual condition, since inassume lang ng ASD ang linear parameter. Pero kung ang inyong diagram ay hindi na linear, nagkakaroon ng curvature. So, hindi na applicable yung dating equation. So, therefore, nagkakaroon ng overestimation. So, it is already accepted by the code. So, next video lecture, most likely, we'll discuss what if hindi naman compact yung flange. Or rather, pwede naman compact yung flange, pero bakit kung yung web naman ang naging non-compact, so ano gagawin natin? So, that will be one of the next video lecture to watch out. So, and also what if full built up yung section natin? So, how do we qualify? So, that will be our next agenda for discussion. Okay, so thanks for viewing. I hope you learned something new today. And if you have any suggestions or questions to this discussion involved, so and also to the future discussion, so please leave your messages in the comment box below, and I would love to read and comment on your questions or maybe suggestions to the betterment of my video lectures in this YT channel. So actually, this channel is intended for the viewers or learners who has the heart to learn. So in all walks of life, maybe he's a student, maybe he's a curious student to learn topics, maybe he's a professional that he wants to go back to the fundamentals, or maybe my colleague that is also a professional but need to recheck his concept by reviewing this discussion, and so on. So I'm open for suggestion, and again, as our tradition goes, you have been Eurorized, and see you in our next video lecture.